My name is Rafal Sztejna. I'm a software architect at Intel. This is my colleague Mariusz. We would like to talk to you about the Swordfish implementation in rack scale design today. And we will start with the code availability. We'll show you the quick overview, what is really the rack scale design, and then we'll deep dive into the details of how the Swordfish integrates with the RSD concepts. And what are the proposed enhancements on top of the Swordfish that has to be done to fully utilize it for example, NVMe over fabric pooling. So let me start with that statement that all we are doing within Intel for rack scale design is a part of open source. We release it on the GitHub, which you can access at any time. And all the, let's say, presented in this workshop. Actually, we're running a workshop tomorrow. Feel invited to it. And all the, let's say, code that is contributing to the workshop is also placed on the GitHub. So let me start with RSD overview. So first of all, I would like to tackle the problems of the, let's say, current data centers, and some of the problems like are the fixed ratio of the compute, storage, and memory. Namely, you have the server as a single, asset. Once it gets broken, the maintenance is costly because usually the full servers are being replaced in a data center. Also, so it's really expensive refresh and scale out, while the only specific server components seem to be failure prone. Outdated software interface in the data center. So everything is, let's say, server side still IPMI based. The BIOS, UEFI BIOS is just one of many firmware components on the board that needs to be replaced, and there is no unique process to do the firmware updates. And the hardware provisioning is very cumbersome. You have different environments which use different means to do the OS provisioning. So they run all sorts of PXE-based Linux utility images that run some simple diagnosis and send all the hardware asset characteristics to the, let's say, the central repository. And only then they change the boot order around the actual workload OS provisioning. So, and actually, which was also already stated in the sources that we provide here. So the most of the challenges is like the utilization of the equipment, the inefficiency of the IT operations, right? And there is a 35 people hours per rack update in each data center on an average. This is why we bring the Intel rack scale design. In all the, let's say, SNIA topics that are happening throughout those couple of days, you see a lot about the data plane. Well, management plane is also important. And the rack scale design is a management industry architecture that provides the composed, disaggregated infrastructure that is built on modern and open standard. And those open and modern standards are namely Redfish and the Swordfish. Swordfish is actually the plugin to Redfish. It augments the Redfish data model with the storage services part of this. So by bringing disaggregated, composable, interoperable architecture, we allow for an increase of agility and decrease of the TCO in the data centers. Now let's go to the details how we approach it. So first of all, on the left we can see a rack which is composed of the pools of the resources. And end goal would be that the compute pool of the resources is also further disaggregated into the pools of the memory, processors, right, and NICs. But we are not there in the technology in the world currently. So the compute is a collection of the servers, right? We also have a pool of the storage assets in the storage enclosure, and some accelerator drawer, for example. And what the, let's say, Intel RSD does, the RSD is able to discover all the assets in the data center, expose it to the orchestration DC admin, DC owner, and allow for composability of the resources into logical entities. For example, at some point you can specify orchestration can request from the, let's say, Intel pod manager, and the pod here is a collection, arbitrary collection of the racks. So Intel pod manager can manage 1 to n racks. And orchestration can use this single point of management to request a compose node A compose node is a logical entity that aggregates disaggregated hardware. For example, give me a server with that amount of the memory and the local storage, and also provide me, let's say, 2 NVMe over Fabric volumes to this server, which are remote to the server we're requesting. So the pod manager, what it does, it actually based on the topology of the pod asset inventory, it finds, identifies, and allocates specific hardware components and provides to this very user for the exclusive use case to run all the sorts of workloads that orchestration can desire. And also, providing the compose node as a logical entity allows the orchestrator to do the management of this node from one single point. For example, power management, changing boot order. It can happen through the pod manager compose node entity. Now, so we covered the portion of having disaggregated and composable assets that can be scheduled by orchestrator, and the life cycle is up to the orchestration, because we support creation, deletion at any time. Now, the very important portion is interoperability, and this is very important in the world of APIs today, that everything is fragmented. So if you look at the study, REST covers 70% of the use cases in API business, but REST itself is just an architecture concept. It doesn't provide any standard data model. Instead, it provides plethora of data modeling, like OpenAPI, OData modeling, and all sorts of let's say environments to model the business logic. But when it comes to the modern data center, we need a standard data model. That's why Redfish was picked as the IPMI replacement from DMTF. That is, previously it was server-centric, but we're trying to bring it to the data center level. And this is not easy part, because as I said, the Redfish is very server-centric. And if you look at the service root of the Redfish service, it's /redfish/v1. So each of the, let's say, nodes that are sitting in your data center will be detected and then discovered by our RSD pod manager and say, hello, I'm this server, this is my path. Now, what the RSD needs to do is to uniquely identify each of the assets and aggregate them into one seamless, let's say, model that is exposed to the orchestrator on the Nordband interface. And there's all sorts of issues with this. For example, you can imagine that some of the, let's say, storage drawer. What is the storage drawer? Actually, it's probably some host, IA host, with the PCI switch, which hosts a bunch of NVMe drives, right? So the storage drawer will expose the inbound service that is actually managing the storage assets, but the BMC of the storage, let's say, enclosure will expose some out-of-band service that shows the compute characteristics of the host. Now the RSD needs to comprehend this and show a, let's say, unique view of the specific storage to the orchestration. So this is just one of many aspects that RSD has to handle. But the overall interoperability part is that we can, based on using one common API, set of APIs, Redfish and Swordfish namely, we can manage the, let's say, hardware from different vendors. And to be more specific, for example, we are able to work, for example, with the servers from Supermicro or Dell, as long as they support the Redfish on the BMCs. And this is, Redfish actually coverage, adoption is progressing, of course, but it's slow, as you probably know. The IPMI still is strong in the market industry. So let me just brief you on the design or architecture of the rack scale. Let me start from the bottom. So I call it like downstream services and an upstream service. We have two layers of the services. One is that pooled systems, or we call them pooled system manageability engines, PSMEs. So these are actually the services that can be, let's say, located physically on some, let's say, control plane of the chassis, or some, dedicated TOR, for example, for networking. These are the services that are co-located with the hardware. They use the native interface to the hardware. For example, if we deal with the legacy servers, then the pooled system manageability engine needs to support IPMI to talk to the hardware, and then it exposes the Redfish interface on top of it. Now, in the newest implementation of the hardware, you have more and more BMCs that expose IPMI, Redfish and IPMI interfaces. Then we don't need this portion, and we can ZBB this one for specific use cases. Now, also we have network service APIs. So imagine the TORs, the top of the rack switches. They run the fragmentation of the networking industry in data center is quite big, right? So there is need to be some unification. What we offer is for now it's as a physical inventory and some basic functions like the VLANs tagging, ACLs creations, and actually let's say detection of the physical topology of the network. We run our agent, let's say, in the TOR. In most of the NOS, we are actually providing for the SDV with Arista the agent that can be utilized right as it is. So, and our network services API, this is some OEM extension from Intel, because as you may know, there is no standard networking for the Redfish so far. There is an ongoing effort to convert the young models to the Redfish schema. In the Redfish community, it actually lasts for quite a while, a couple of years from now. So eventually there was, let's say, identified a tool. There was, built a tool that creates a conversion from the, let's say, young data model to the Redfish schema. This is just that, network is defragmented into many different, let's say, models. And the YANK itself is a data modeling language. It offers you, all the, let's say, whistles to model specific network topology, network service, full data center networking. But then at some point, Redfish needs to take, let's say, a lead and define a number of the YANK models that are converted to Redfish, log the schema, and let it propagate, let it be standardized. So we're counting on this to happen soon. But for now, Intel provides its own extension just for the physical network, asset, let's say, inventory and some basic management operations. Now, we, in the, let's say, storage services, we provide the implementation of the storage service that exposes the Redfish Swordfish API. And this is not sole Swordfish. And you probably already been told by now, because there were multiple sessions on Swordfish in this conference. The Swordfish is extension. This is a plugin to Redfish. It's augment the Redfish, because Redfish has a compute server view of the, let's say, assets, entities, and the storage brings the concepts of the storage pools, drives, volumes, and it differently, let's say, models the storage world. But it also needs some augmentation, which is part of the Redfish, and we as an Intel provide some, let's say, enhancements, which Mariusz will be talking about soon. But the point is, these services are also exposing the Redfish and the Swordfish here. And of course, we provide the chassis management API, Redfish-based, using the chassis and the management entities. We provide the power and thermal management capabilities in the chassis. Now, if you take a closer look at this is the Redfish and Swordfish, right? All the way through the, all the domains. Now, on top of the services that can, and to give you a concept, for example, this pooled system manageability engine can run in each of the servers if this is run on the BMC, for example. Or it can run on the chassis, which hosts up to 4 servers or more, depending on the implementation of the hardware. But there will be multiple of those services for each of the domains. And what the pod manager does, it aggregates it and shows the seamless, let's say, API on Norbound interface for end user and orchestration. So it first, let's say, role is the asset management, and I already talked to you about this. Let's say, it needs to uniquely identify all the systems, build some abstraction layer, because if you have the collection of the computer systems, and you have, let's say, for the computer system, you need to show them to the user in some unique way. So you need to create the collection of computer systems. And within this collection, each of the computer systems has to be characterized by its UUID that got from, ideally, it goes from the FRU. And Pod Manager also offers the pod-wide composed node management, and this is the notion of the composability I was talking about. So taking, let's say, taking the request from the end user, hey, give me a compute server, right? To, hey, give me a compute server with X amount of the megahertz of a memory and the local storage, right? Or give me a compute server and also give me the, let's say, remote NVMe over Fabric volume with it. This is the composed nodes management that Pod realizes. And it also provides the Fabric management. And important from the management perspective, because our work is about the management of, and it's mostly done via out-of-band mechanisms. The Fabric management is important because, for example, for NVMe over Fabric, you need to identify and you need to create a binding between the initiator host system and the volume which resides on the target subsystem. And this is not taken care of by the NVMe.org standard. They only define the, let's say, discovery service, but there is no notion of the, let's say, Fabric management. And the, let's say, Pod Manager and the Intel with RSD provides this. It was actually submitted to Redfish, and it's called Common Fabric Model. And also for the storage management, the Pod Manager needs to comprehend all downstream storage services that expose the Redfish and Swordfish combination and provide them to the end user. And of course, on top of the RSD Pod Manager, there are all sorts of the end users, admins, the orchestration, let's say bare metal as well as a virtual one based. And there may be cases that some of the, let's say, customers want to do some proprietary, let's say, management functions as opposed to using the Intel Pod Manager. They can actually access any of downstream services because they expose the, let's say, regular Redfish interface. Now I just briefly will talk about the architecture of the storage service that Intel proposes as a reference code. So we divided the storage service, and this is actually on the normal interface, it exposes Redfish Swordfish API. Of course, it has the asset manager because it needs to, let's say, detect all the assets, the storage-related assets in the storage server and expose them on the API. There is some database required for persistency of the data across the resets. And three main storage management functions within the core application, or as we call it, REST server, is, let's say, target management. And for targets, we mean the NVMe over Fabric targets, as well as iSCSI. And the storage management also needs to, has the interface for logical devices. Most utilized one is the LVM. There may be some, let's say, Ceph-based device management. And also we do the physical device management. For example, one of the options was that one of our volume managers is that realized, such as we utilize the GPT partitions. So we try to be as close to the hardware as we can. But also we build on top of LVM. It's probably most utilized in the industry. All right. So now let's move to the NVMe over Fabrics using Swordfish. And I will show you some, big picture. So the Pod Manager, which I already talked about, is a central, let's say, service from RSD standpoint. It needs to, let's say, work with the discovery service and the storage server. And let me give you some brief overview. For those familiar with NVMe over Fabric standard, discovery service was defined to provide, let's say, some discovery from the, let's say, initiators, from NVMe over Fabric initiators. There is a very well-defined mechanism, which namely is get log pages with the discover parameter, which let's say any host-based initiator running on the compute server has to call to find out lists of the targets that are, let's say, assigned to specific compute server. Now, this discovery service, and by the way, NVMe.org doesn't specify how this discovery service is being configured. What is the management interface? So RSD provides so discovery service, as defined by spec, exposes the, let's say, endpoint on the, let's say, RDMA stack. But what RSD does, it provides another mechanism, which is Redfish-based API that the pod manager uses to configure the discovery service. And the pod manager does it in such a manner that when the request from the orchestration comes, hey, give me the compose node and assign NVMe over Fabric volume. So what pod manager does at this moment is it identifies the hardware assets, and then it configures the storage server. It creates the volume, or it allows user to create a volume. And this volume is assigned specific network qualified name, which in the world of the NVMe over Fabric is the, let's say, main identifier. This NQN, and also the pod manager tells storage server, hey, for this NQN, the only host that is allowed to contact is this one, and it describes the, let's say, host of the compute server by its own unique NQN, which is based on UUID. This is our implementation. Now, what pod manager also has to do is has to configure the discovery service, which in this scheme of things, this is a proxy. Because at the end of the day, you have the client host that is running on the compute server allocated to specific user, and it's provisioned by specific user, so we don't have any mechanism to influence what's running here. So the client host needs to use the, let's say, the standard tools like CLI, NVMe CLI, to let's say, query the discovery service for a list of the targets that were assigned to this host. Now, it will get the specific NQN that pod manager assigned to him based on the user request. And from this moment on, the client host can do the NVMe connect command directly to the storage server, providing the network qualified name of the volume that was exclusively allocated to the specific host. So this is, in a nutshell, how this manageability portion of the NVMe over Fabric works. And let me pass the mic to my colleague Mariusz, who will brief you on the more details on the Swordfish implementation.
Okay. As Rafał mentioned, my name is Mariusz Krzywienski. I'm also working for Intel for RSD project. And I will give you some overview about the Swordfish implementation that we did in RSD that was released recently. So in our implementation, we implemented some subset of the Swordfish resources. Not all of the resources, but the most important from our point of view to implement the NVMe over Fabric functionality. So obvious resource is the storage service, which provides the storage management functions. We implemented drive collection, which was not defined in the Redfish standard. This is something that was provided in the Swordfish. Similar for the endpoint collection, we have this collection to gather all the endpoints used for the initiator and targets. We have a storage pool and storage pool collection. A storage pool provides you the pool of the storage that you can use to create volumes. In our implementation that is currently available, the storage pool equals one drive. So the storage pool is created on the single drive. And of course, there is a volume. Volume is the main resource that is used in NVMe over Fabric, because the volume is provided to the client, to the initiator. There is an endpoint called capacity, so you see how much capacity is available for the data, for the metadata, and so on. And the last one is the storage replica info. Storage replica info is used to allow user to clone volumes. So if you create a volume, you can clone this volume from the other to have some replication.
Why is storage pool limited to one NVMe drive?
Because we are using Linux kernel functionality, and in the Linux kernel there is no functionality to do some write zero. We are not using write zero to gather more drives to create bigger pools. This is the This is the approach that allows you to quickly provide this functionality. In future, we are going to use SPDK, which is also providing NVMe Fabric functionality, and SPDK allows you to create pools of the bigger than the single drive.
So you don't currently use your VLOG features?
Not now. Not now.
So you don't have
Class of service is not implemented yet. We are going to implement in the future to provide some IOPS limitations and something like that. Okay, so now I'm going to go into some details. So to create NVMe Fabric connection, you need to do some steps. First step is to create endpoint using the volume. So in the connected entities property, you need to provide the link of the volume that you want to use for the for this endpoint and the role. In this case, this volume will be target. Also, I create some color coding here. So the green ones, green properties are used for the host server. So when you maybe the host server is this storage server, and discover service is the entity that provides you information about the connections. Okay, so the red ones are shared for the discovery service and the target host. For the discovery service, you don't have this link, so you cannot provide this link in the connected entity. The next very important property is the NQN in the section of the identifiers, because you need to identify this remote volume somehow, and in NVMe Fabric we are using NQN identifiers. Next section is the IP transport details. IP transport details provide you information how to connect to this remote target, this volume. So you need to have an IP address and port on which you are going to have this connection. So this is the important information, and also the protocol that we are going to use. In our implementation, we are using Rocky V2. And we did some extensions to the resources defined by the Swordfish and Redfish. In that case, in the endpoint, we added the link to the zones. So it allows you to, yep.
Sorry, but as far as populating that itself, getting the information from the device, how do you actually make a query on the back end? And also, if the NVMe line when that comes out, does it answer just subscribe to it? Because you still have to query the device to populate these fields.
Okay, so if you're creating endpoint, you don't need to provide every field. You can provide only the link to this volume that you are going to use, because you need to point which volume you would like to connect to, and you need to provide NQN as an identifier of this endpoint. Yeah.
Agreed, but you still have to query whether it's sitting on Rocky or sitting on PCIe bus, right? So you still have to query the device at some point, at least to get some of the fields populated.
Yes. So in our case, you don't need to provide IP transport details. For example, the service can get these details from the hardware itself. It knows what the network card are inserted, and if it's Rocky, it gets the IP address and provides this IP address for you. If you have a multiple network interface, then you can provide these details to show which interface you want to use to connect. Okay, so I was talking about the zones. The zones link provide you a quick way to distinguish in which zones this endpoint is used. Zones is the logical entity that connect the initiator and the target endpoints. And also we are providing the links to the interfaces, to the network interface cards, to get information which interface is used to provide this endpoint functionality.
So what is the role of the zone?
Zone has no role. Zone is the logical thing that connects the multiple endpoints. So you can, let's imagine that you have one initiator and multiple targets. So this initiator is allowed to connect all these targets. Yeah?
So zone is the list of things that can talk to each other. Think of it like a subnet.
Yes. So zones has no role. Okay, and next thing is to create endpoint for the initiator. So as you can see, the list number of the properties is less because the target host doesn't need to know every details of the initiator. The most important are the NQN, once again. In our implementation, we are using the server GUID as a NQN builder. This is important because we need to manage the initiator from the out of band, and the only thing that is the shared between in-band and out of band is the system GUID that is generated by the BIOS. So you can read this GUID from the operating system, make the initiator NQN, and then we are able to make sure that this initiator will be able to connect to given targets, and we can identify it uniquely. And yeah, the zones are the same, so it allows you to know in which zones this initiator is used. And you need to also provide role that this endpoint is acting as an initiator in this case. So if you have an initiator endpoint, target endpoint, then you can create zone. You're taking this endpoint, create zone, and this is the signal for the storage server that it needs to create NVMe subsystem. And in NVMe subsystem, it will expose the targets, NVMe targets, and it also create the host, and the host will provide information which initiator, which NQNs are allowed to connect to this subnet, subsystem. Okay, so that was the how the Swordfish is used for the creating NVMe-oF fabric, and I would like to tell you about the enhancement that we find out to be useful for the Swordfish. So, as I said, for the endpoint, we are using the zones that provide the information when this endpoint is used, and the list of interfaces that are exposing this endpoint. Also, we added the authentication property. This is mostly used for the iSCSI thing. So we need to provide the CHAP functionality somehow. So we need to inform the storage server that for this particular endpoint, for this particular target, we need some authentication. And I know that Redfish is also working on providing that functionality in the standard. So currently we are using this authentication only for the CHAP, for the iSCSI, and for the NVMe fabric we want to extend it to use public key-based authentication, so the both sides of the communication channel can authenticate them mutually. The volume is the basic thing used in the storage server. So in the volume we added the list of endpoints, so it allows you to quickly identify which endpoints are created for this volume. In RSD we have a limitation that the single volume can have only one endpoint because we are not support sharing of the volumes right now. We also added the bootable flag. This is also used for the iSCSI, and NVMe-oF Fabric doesn't support booting from the NVMe-oF Fabric. At least I don't know about that feature. So we are able to provide information to the storage server that this volume is able to be to provide bootable functionality. So you can boot from this iSCSI target. And we also provide some metrics to the volume. This is used for the telemetry purposes. You can get some information how this volume is used. So, like how much capacity is used, how much is left, and so on. And in the storage service itself, we added link to the manager of the storage service. It was very useful for us when we wanted to find out who is managing this storage service. For the drive, drive is hosted or owned by the Swordfish, by the Redfish, but we added some enhancement to the drive. We added the firmware version, which is important from our perspective because we need to know which version of the firmware is installed on the drive. We added the link used by, which provides linkage to the storage pool when this drive is being used. This is more important if you have multiple drives per storage pool, the feature that will be supported in the future. And we added the telemetry metrics that provides some information about drive, like temperature, number of units read, units write, the smart data from the drive. Okay, and you probably saw this slide many times today, but I personally want to invite you to the workshop that is being provided tomorrow. We are going to provide to show the RSD implementation live, so you can see how it works, how it is implemented. You can see code, you can play with the NVMe-oF Fabric implementation and ask questions if you have any question about this implementation. Yeah. Okay, thank you very much.